All right. Our closing talk representing data for the entire conference. Well, mostly. There was some little bit here and there. No pressure.
No.
It's just data. I mean, come on.
We know what you've been doing. All right. Thanks a lot. And first and foremost, thanks a lot for attending. And because I'm the last speaker, actually, thanks a lot to Luke and all the organizers for setting this up. It's been a really, really great thing. And thank you all for actually staying to the last talk and actually listening to what we have to say. So as Luke has mentioned earlier, I'm going to talk about how do we build solutions for data processing with microservices using projects such as Spring Cloud Stream, Spring Cloud Data Flow, and Spring Cloud Task, which are, let's say, our microservice-based solutions for what used to be called, we don't call it again, big data. I prefer the term data-intensive applications, right? And generally speaking, the spaces we're talking about is, have it here, tons of different data sources producing, well, data that needs to be moved into different types of stores, that needs to be analyzed, that needs to be handled. So we're talking about use cases such as data movement, data import, data export, analytics, right? And so in this space, the classic approach has been batch processing, right? And some of the use cases that you see there are still very valid. Right? The batch processing used to be, has been for a long time, the standard approach for a number of reasons. It's much more efficient. It's cheaper to process, to gather all the data and process it at once, right? And as I said, some use cases just lend themselves to this type of solution, like extract, transform, and load, right? Things like account reconciliation, things like payroll, which happens essentially at specific periods of time, right? Machine learning, for updating a model, you need to have all the information about how that model has performed over a given amount of time. And all of these have very specific requirements, like periodic execution. They talk about, they operate with finite data sets. You need to be able to retry, like a failed batch job, for example, because it was trying to move data to a store that wasn't online or available at the moment. Needs to be retried and basically kind of be able to keep track of of how far it went before it failed, and they need to be stopped, restarted, and so on. Right? And the reality is that in the past years, right, there's been an increased tendency to move these types of solutions from the space of pure batch processing towards more real time. Towards more, instead of what's being called stream processing, essentially, right? And the motivation for that have been two. One was basically because we could. It was cheaper, to move data. It's cheaper to store data. It's like we have much more capacity, computing capacity, memory capacity to actually handle data as it arrives, right? The second motivation is business. Now, because we can do it, we actually want the results as close to the moment when an event happened, right? Fraud detection, right? We used to look at your credit card statement and figure out whether you had any fraudulent transactions. Like with the volume of transactions that happen right now, that's just not acceptable. You want to know things as they take place. So basically, as let's say, as certain types of problems that used to be the realm of batch processing have moved into stream, that's not to say that all of them have to move there, right? Some of the use cases that I mentioned are a perfect illustration why you still want to do it, and some of them basically, in some cases, it's just still cheaper like some certain workloads just don't lend themselves to paying prime computing time. We can just run them at night on where it's cheaper, on where basically when resources are available, right? So what I'm saying is that there is still a very valid case for doing batch processing, and it's still a very, very modern approach. And it's part of the solution that we're building with Spring Cloud Dataflow. Moving to stream processing, essentially, the use cases there, as I mentioned, are more like real-time, let's say, versions of the batch processing use cases. And besides, let's say, we can process massive amounts of data in real time because we can, there's also another venue by which like these stream processing, real-time data processing use cases come to life, which is problems that have in the domain of traditional enterprise integration moving to this space. For example, take preventive maintenance again. You used to get a notification when something was wrong with a piece of equipment, right? That's sporadic events that needed to be handled as soon as possible. Instead of that, you want to know how the equipment performs before it actually broke. We start collecting data, we're starting sending more data upstream, we're starting processing that data in real time and shaping how the equipment performs and trying to infer in what state it actually is. And these use cases have very specific requirements as well. High throughput, low latency, basically two kind of things that usually need to be mitigated. And apart from the performance requirements of these use cases, there are also other functional requirements. Data grouping. We not only want, typically when these large data volumes refer to related items. For example, sensor data, right? Data from the same sensor, it might be as well processed together, right? Ordering. We really want to make sure that the way in which data is received reflects the order in which it has been produced. If I'm trying to infer, for example, the state of, again, a piece of equipment, I want to know that a specific sensor fluctuated in a certain kind of way. The order of the events actually influences the conclusion that I get from analyzing that data. Time windowing. Windowing by it's basically, when we actually do these types of computations, we really want to narrow down to a very specific. We can't look at data of over the entire amount of time that the equipment has been on, right? So we typically want to say things like, I want to process data from the last 5 seconds every second, right? And this has also led to a shift in the way messaging middleware has been designed. Like traditional messaging systems, which more things like RabbitMQ, for example, or WebSphere, are still a valid mechanism for transport. But actually, what we've seen again in the past few years is essentially the rise of, let's say, more simpler and more oriented towards the task messaging paradigms. Take, for example, Kafka, which is essentially a log, right? This model has actually become very prevalent. And why is that? It is because it satisfies some of the requirements about data grouping, data ordering, right? Things like that. So in this context, and given these types of challenges, or given these types of use cases that we're trying to address, we're trying to promote a solution, and we're trying to promote the idea that microservices are the right way of building systems that try to solve this type of problem, right? And we know that from our experience, because how many of you have been using or are familiar with Spring XD? Not very few, so I'm not going to enter in many details, but Spring XD was a data processing platform built on top of existing Spring projects. Spring integration, how many of you have been using it? A few. Spring Batch, a little bit more. The idea was that the Spring ecosystem itself has a lot of powerful tested components that can actually be part of a data processing solution. Spring XD was essentially a platform in the sense that it allowed you to write encapsulated components that ran in containers that the platform managed. And this is basically where we realized that while we were doing this, realized that the microservice approach was much better. It's no coincidence that the transition from a platform to a microservice model happened around 2015, when Spring Boot and Spring Cloud reached maturity and started to gain wider and wider adoption. It basically validated that the cloud-native microservice model was a valid tool for solving all kinds of problems. And in our case, what it did, it enabled us to put together this platform that essentially consists of three major projects. Spring Cloud Data Flow is the orchestration engine that takes care of deploying and organizing microservices in various topologies. And we'll actually see a demo of how it works. The programming model for real-time streaming of Spring Cloud Data Flow is Spring Cloud Stream. And we're going to see actually in a little bit detail how it works. And the programming model for batch is Spring Cloud Task, right? And all three of them have in common the idea that all the handling of the data, all the ingestion, all the analytics, all the computations are done by standalone production-grade applications, right? And this comes with a number of advantages. The traditional advantages of microservices: bounded context and development agility, immutable infrastructure, failure isolation, right? I don't want, for example, one component to take down the entire pipeline. In the case of data processing applications, it's even more interesting because the fact that we can run applications as separate instances allows us to scale, allows us to allocate, for example, to control how much memory each of these steps of the process gets. A data enrichment component, for example, needs more memory, and a component that does some intensive computations may need more CPU. An application that basically, like a step that just ingests data as fast as it can and writes it to HDFS requires network, right? So just having multiple instances for being able to deal with multiple network interfaces is a requirement good enough for breaking things down into multiple instances and actually running them as independent components. The model that we've adopted is basically of event-driven microservices. So all the communication between these instances is done through messaging. We favor this model greatly because it increases the decoupling. You don't need to know where if the other application, the application you're communicating with, is down, you don't even know whom you are sending your messages to. It improves discoverability because it allows, for example, pub-sub models where new components can be added to the pipeline just by connecting to the intermediate steps and receiving data. And in the context of, for example, in data consistency, it allows things like eventual consistency between applications as an alternative to distributed transactions. So one of the goals here is that one of the things that we actually noticed in this context is that there are very, like when it comes to these types of applications, whether you do data processing, for example, you do event streaming, they're very similar. And you will see actually probably one of the best examples is that how many of you have attended Chris's demo for Spring Tool Suite at lunch? Right? That's one application, that's been one application built using Spring Cloud Stream. There was nothing data intensive in that application. It's the same, but it's the same component, it's the same idea, it's just a simple message-driven model that can be applied for different types of solutions. And the last aspect, and I probably can start delving a little bit into the details and to the demos of this solution, is the cloud native aspect of it. Because we have microservices, because we have applications, because we want to run them, because we want to ensure things like resiliency and easy scaling, right? And we want to make sure that their health is managed, right? That is a more complex thing to do if you do it by yourself. So that's one of the reasons why distributed systems are hard. Now, fortunately, there are platforms. There are a lot of platforms out there that support this natively, like take Cloud Foundry, for instance, right? It manages your applications. It allows you to scale them under your control. It restarts applications if they fail. So basically, all you need to do is just to make sure that you go and deploy them. And that's basically repeated like to some degree or another in other platforms, like in Mesos or in Kubernetes, with less or more capabilities, right? Yarn, for example, doesn't have any, doesn't necessarily have any routing capabilities, but it's a resource scheduler. It's still can use it for running loads. So relying on the native aspects of the target platform is kind of a natural choice for this type of thing, especially when you try to create like really sophisticated data processing pipelines with large number of instances. So in a single sentence, we want to be able to do something like this. We want to be able to run an application that receives data on HTTP and ingests it into a file, right? And for that, I'm just going to start a local instance of Spring Cloud Dataflow, right? And Spring Cloud Dataflow, as you will see in a bit, actually has a number of different ways by which you can control it and interact with it. It has a web UI, for example. But what I'm going to use is the Spring Cloud Dataflow shell. So that is I'm a Unix-like command line shell. Let me just scroll up a little bit. And in this shell, it has different commands. I can deploy and create streams or run tasks. So in this case, I will want to create the pipeline that I've just described. I will need to register a number of components. So the way it works is that Dataflow actually manages a fleet of installed references to full-fledged Spring Boot applications, right? And I can use these references to describe data pipelines. In my case here, for example, I'm going to describe such a pipeline that runs over Kafka. So I can do something like this. Stream, create, HTTP file, I'm going to define it. I'm going to create an HTTP endpoint that listens to the port 9000. And writes to a file in the directory file. And I'm going to deploy. And what happens is that I have Kafka running on my machine. What happens here is, if I'm running JPS, you will see two components, two applications running, file sync Kafka and HTTP source Kafka, right? These are the two components of my pipeline. They run on my machine, and if I'm posting data, for example, let me just clean some data from my previous executions. I can post some data here, so I can just so you see the message basically being ingested in the file, right? And I can post another message. And you can see it basically reaching the file. And it's a very simple example and doesn't do too much. And the exciting part about it is that, as I said, there are two standalone applications coordinated through this deployment mechanism, talking to each other through Kafka, right? And everything basically happens through a simple topology description, which is the stream definition, right? So let's go a little bit inside and see how exactly these applications are built, right? In our case, these applications are built using Spring Cloud Stream. So Spring Cloud Stream is essentially our event-driven messaging framework. It's built essentially on top of Spring Boot and Spring Integration. Each of them basically contributing, Spring Boot essentially contributing with its capabilities for building full stack standalone applications and everything that derives from it. So the management of dependencies, Uber jars, configuration through different mechanisms, command line environments, and so on and so forth, right? Everything that you get from boot. From Spring Integration, essentially, it's getting the the messaging infrastructure, the pattern implementations, and the enterprise connectors. As you will see, there is an entire ecosystem of applications built from Spring Integration components and Spring Cloud Stream for data processing by Spring Cloud Dataflow. But Spring Cloud Stream tried to be a little bit more than that. So just making it easy to use Spring Integration with boot is not actually the most useful task. It tries to build some primitives that we find that are typical for this type of structure, for these types of applications. So I'm going to try to get a little bit into detail with that. In a nutshell, a Spring Cloud Stream application consists of a middleware agnostic core that communicates with the outside world with a number of inputs and outputs, right? It doesn't know about anything else, doesn't care about anything else. And this kind of uniformity is basically what makes it capable of plugging in these components with each other and actually building some very, very complex, very wonderful infrastructure, right? Really complex processing topologies. Now, if you actually go a little bit into more details, the abstraction here is that every channel is created and managed by the framework and injected into the application and is wrapped with what we call a binding. There is a component in Spring Cloud Stream called a binder that actually takes care of connecting these channels to the messaging middleware. And this binder actually is configured through Spring Boot properties, right? The binder abstraction is basically what makes possible to write applications that work the same on Kafka, with Rabbit, with, I don't know, ActiveMQ right now. For example, we have Google PubSub, an implementation. So you just take only one of the examples, you just swap the binder, and that's it. You can actually have an application that works and interacts through another middleware. Right? The programming model essentially consists of declaring your external outputs, adding the binder to the class path, and you're done. And so if you look at it, it looks something like this. This is, for example, the simplest possible processor that you can create, right? Enable binding essentially gets as argument an interface. Let me just pull up the processor interface for a second. So if you go, for example, and take a look at the processor interface, okay, the processor interface, for example, has two channels. One named output and the other one called input. And the reason why it doesn't declare anything explicitly is because it inherited it from two other interfaces. But the idea is that at runtime, the framework will actually instantiate them and connect them to the messaging system, right? And make them available to your application. So basically, this says, well, I'm going to listen to the input channel. I'm going to receive everything that's being processed. I'm going to receive all the messages. I'm going to extract the payloads, and I'm going to convert the result to uppercase and send it back, right, on the output channel. So it's a very simple transformation. What's interesting about this is, and tying a little bit into the discussion about reactive processing that's happened earlier, is that we've found this model to be suitable for, let's say, certain types of scenarios, especially when you process message by message, like do these type of message by message computations. But when you think of it, when you think of these inputs and outputs as actually as continuous streams of data, it is probably a better, like the functional model of that's proposed, for example, by Reactor is a much more like suitable approach. So in that sense, we allow both approaches to be followed. So we can write, for example, handlers that are essentially taking each message, handling it, and returning it, whatever we want to do with it. But you can also write processors that are actually processing things in like as a flux. And while this example is just a simple transition here, just like it's still kind of not very different in a way. Still, each individual message is handled in and by itself. When you look at things like handling multiple returns, for example, or filtering, or doing something else, then the functional model becomes much more compelling. Like imagine that I wanted to filter something here. What do? Do I return a null? Do I return an empty value? How do I tell the application that I want to do that there is something else going on? And if you add something even more complex, like applying something like stateful operators or grouping and so on, you will find that the APIs from like the reactive APIs and reactive, like in particular the operators, for example, of Flux, the functional operators for windowing and transforming, allow you to really express the notion that this is, for example, like this is converting an inbound flux of words. It's grouping them by by their value, and it's counting them, and then it's returning their count. It's not the easiest API to read, especially if you're not familiar with functional programming, right? But once you learn it, it's actually very correct and expressive in and by itself, right? So that is an alternative in terms of a programming model that we provide. So the idea is that built on top, like built in this manner, your applications really become the classic pipes and filter structure, where each component actually receives, in the case of data flow, for example, it really, it standardizes around 3 different models, like 1 input, 1 output, and both an input and an output. Right? In the general case, you can actually have as many inputs and outputs as you want, right? But the point is that having these interconnection endpoints and having them just managed through configurations actually allow them to chain these things together into really pipes and filters structures, right? And I can show you a quick example, right, of something like that. So normally this is, I do this as a live demo, but in the interest of expediency, I'm just going to run the result of my rehearsal. So basically what I built here is an application that produces sensor data, right? So I'm generating this stuff periodically, like I'm using a polar, essentially, an inbound channel adapter with a polar from Spring Integration for producing sensor data. This has a default of 1 second, so every second this method will be invoked and return some data, right? And what I'm doing here is that the only components, the only really dependencies of this application are the test starter and the Spring Cloud Stream starter for Kafka, which adds the Kafka binder on the class path. And this is actually produced by something, it's really produced through Start Spring IO. So if we had time, we could build this from scratch in a few minutes. But I'd like to show you a few other things, so I'm just going to run it. The point is that this application declares a binding. That's this application, which was it? It's a producer application. Declares a binding of the type source, and then it has a configuration. And the configuration basically says that everything that's produced on the output channel is produced on the sensor data destination, which is the sensor data Kafka topic that I'm going to write to in this case. If it was Rabbit, it would mean something else. It's an exchange. And the other thing is, I declare the content type of the produced data, which in this case is application JSON. As you notice, I am producing POJOs. I have to marshal them in a way. The default strategy is to marshal them using cryo, right, in serialized format. But that's not exactly very usable. Especially with microservices, you don't want to start sharing code, not even types, between applications. What happens if I want, for example, to change the format of the data? We'll talk about that in a minute. Right? So that's basically hold on for a second. I started this application, and it started basically, it just goes on and it produces, actually no, this is the logger, sorry, this is the consumer application. I will start the producer. I need to start the producer first. The consumer application is pretty much the same thing. It has a different annotation that has an input channel, and essentially, when it receives data, is actually it is actually sending it to this method, right? I declare here, I'm saying I'm listening to the input channel. And the interesting thing about this example is, if you notice, this type, like receive sensor data, is actually is not a type that's shared between the two. The framework actually takes care of unmarshalling the data based on the fact that it knows that it's JSON. How does it know? It's basically every message that goes out has a header attached to it that tells the framework what type is it. And you actually, the nice thing here is that we use the infrastructure from Spring messaging to do this conversion. So it's not even something Spring call stream specific, right? We try to be as consistent to other things like WebSockets, right, in this particular case. So if I'm going to the logger, you can see that the logger is basically logging everything that's being received. Let me see if I can make this a little bit larger. Yeah. Anyway, basically, two simple applications talking to each other over Kafka, right? Very, very basic stuff, doing message conversion, doing all kinds of things. Now, beyond simple pipelining, we actually do other things in Spring Cloud Stream. One is essentially that, imagine that you have this like pipeline built, right? And you want to add new components here. What do? Obviously, you would have to have a strategy, for example, for sending, like, for example, this average calculator, right, in this example, would have to send its results to two other components. You just want to attach something to this structure. One option would be to modify the application and make it basically send data to two separate destinations, right? That's not good for two reasons. One is basically that you will never know how many destinations you will have, so you want to do that kind of change. Second is that essentially it's increasing the traffic, right? So for this reason, all the destinations through which these applications interact are publish subscribe. So the model is basically publish subscribe by default, right? You can add more logical applications easily to your pipeline right now. The challenge with that, though, is that if you're trying to scale and you have a publish subscribe model, what's going to happen is that by default, everyone will receive the same set of messages. So for example, if I add two new components here, like for example another average calculator or another HDFS sync, I will get, all of them will get the same, will get a copy. And that's not very good because I really don't want, the reason why I'm scaling is because I want to distribute the load, not to increase the load, right? So this is why we actually have a concept called consumer groups. It's borrowed from Kafka. How many of you are familiar with Kafka? Right. So you recognize the concept. It's the notion that you can declare what applications are part of the same logical group, and within that group, everyone's a competing consumer. Outside that group, between the groups themselves, the communication model is publish subscribe, right? So that's also like a native feature of the framework. The other thing that the framework provides natively is partitioning. Partitioning is also a requirement because in these types of structures, the simple fact that you do load balancing, again, may not be enough. If you have related data, like for example, if you try to calculate the average value of a sensor, you don't want that value to be, you don't want the values to be basically scattered across multiple instances. You want related values to always go to the same to the same instance. So Spring Cloud Stream essentially allows you to declare your partitioning strategy for the data. And the partitioning data is always partitioned at the producer. So basically when you say, I want to produce data here, and this is basically my partitioning strategy. In this case, for example, in the sensor example that we had earlier, it would be by sensor ID, right? In some other cases, I can have other logic. Like there is an entire, a number of options that you have. Spring, like spell expressions, for example, is the simplest one, or you can implement your own classes. But again, partitioning is a first-class citizen. And there are a few other things, but we are kind of late, and I strongly encourage you to take a more in-depth look at, for example, things like schema support, which essentially allows you to manage and evolve your applications in your topology. So natively we support, like in a very short description, what happens is that you've seen that, for example, and I can declare that the type is application JSON and send that data over the wire, and it will be converted to JSON, and receivers can actually convert it back. JSON is a good and portable format, but it's slow to parse, and it's verbose, right? And data-intensive applications, for example, require much more performance serialization protocols. One of them is Avro, right? And Avro has this great capability that it can store what we call the writer's schema, which is what was the schema, what was the data model at the time when the data was written. The reason why that is good, because if you work with serialization, you know that once you change, for example, the structure of a class, you might not be able to read your serialized data back. And that is a problem, especially in microservice infrastructures, because you can't just have, like if you cannot deploy or redeploy an application and change its data format, right, and all your other applications will crash because of that, then you've solved nothing. Right? You've created a distributed problem. What you want is to have the ability of changing just part of it, produce data in a new format, and essentially have the ability to read it back at any consumer. So what happens is that we provide this ability to include references to the original schema of the produced message in headers, and the consumers can actually retrieve that and extract the message, right? So speaking about this, like if you've seen, as I said, if you've seen Chris's example and my example, you see that actually we manage these applications through Spring Boot properties, and that takes us pretty far. But if I have to do this, right, like this works when I'm trying to connect to applications and I try to make them talk to Kafka and so on. If I'm trying to do this for a much larger topology, then this becomes very, very complicated. What if I'm trying to, like, it's easy to launch two applications manually on my machine. What if I have to have, like, if you count here, I already have 5 different logical applications. I have multiple instances. Each one of them has to be configured in a way. So I have to decide on the different, like, on the intermediate topic names and so on and so forth. Like, managing these types of large-scale topologies is basically is untenable, right? So this is why, even if we have this application, this microservice model, we need something that can actually orchestrate and manage its deployment, right? I don't want to go and deploy everything manually. I want to start things at once. So this is basically where Spring Cloud data flow comes into play. Right? Spring Cloud data flow has a number of like, plays a number of roles, but the most important ones are 2. It helps you define the topologies of your applications. If you've seen, for example, my earlier example, I've just said I want to pipe data from an HTTP endpoint to a file. right? When that happened, actually what it does is it tries to resolve this information. You have different types of artifacts that can be resolved, mainly Maven, like jars, and you can use like Maven, or you can use HTTP links to actually resolve an Uber jar. It also resolves Docker images for platforms that require Docker images to run, like Mesos, for example. And it starts them, and it basically defines, like it uses conventions for example, for connecting them, right? So I don't have to write anything. I didn't have to tell them that my two applications have to use this and this Kafka topic, right? Dataflow actually took care of that for me. And the other, like, apart from doing this, like, conversion from, like, topology specification in DSL form to an actual graph of running components, the second thing that it does, it really abstracts the job of deploying on different platforms. So there is another project underneath that it consumes called Spring Cloud Deployer that actually acts an even more lower level API for deploying to different platforms. But the point is that using those abstractions, you can plug in implementations for different target platforms. So the same server, essentially, or I shouldn't say the same server because it's a different build. It's a build with a different dependency. But the same logical component, right, that handles like the interaction with the shell or interaction with the UI or with the RESTful endpoints, right, can talk through an adapter layer either to Cloud Foundry or to Mesos, for example, or to Kubernetes or to Yarn, right? Or even OpenShift, right, which is essentially Kubernetes. So when you actually deploy such a stream, you have basically what happens is that each of these components is essentially deployed inside the platform with different specifications. You can specify, for example, how many application instances you want. You can specify performance criteria and so on, right? And it can actually use the features, like the native features for partitioning, for example, instance count management in Spring Cloud Stream, to actually describe, as I said, graphs with like scaled up components. Like, for example, I want to have 2 HTTP endpoints. I want to have 3 processors that do actual work, and I want to write that data to HDFS through 4 separate instances, right? Again, I don't want everything to be scattered, right? So basically, the way to actually indicate where each piece of data should go is done really through deploying what we call deployment properties. And the deployment properties are basically very simple. You can have deployment properties for the instance count. I can say my HTTP application, I want to have 2 instances of the HTTP application. I want 2 working instances, like 2 workers and 4 HDFS writers, right? And between the HTTP and the workers, data is partitioned by payload ID, right? I can also manage, for example, things like memory, right? Give more or less memory to the different components. I have that degree of control. So let me just show you very quickly, like in counterpart, how the deployment works in Cloud Foundry. So I already have a Dataflow server running, and I can take the same, basically almost this, virtually the same shell that I've been using, I mean a different shell instance, but it's the same implementation that we've been using for the local deployment, and point it to the Cloud Foundry deployment server, and I can create a stream. So I'm just going to use one of my previous definitions here, right? And I'm going to create, instead of writing to a file, I'm going to write to a log, because I also want to show a little bit, I want to see this on my machine. So I'm going to create a stream that basically gets data on HTTP and pipes it to a log file. And one thing you notice is that I don't have to give it, like in my local example, I had to give it a port, right? Because I have multiple applications running on my machine, and I have to make sure that they connect to different ports and so on. In this case, I don't have to do anything like that, because every application will be unique. Every application runs in the platform and gets an HTTP route and an HTTP URL that I can post data to, right? So I'm going to create this stream and deploy it, right? And as you see, the various the applications in my stream. So when I created that stream and I actually deployed it, I see two applications already created in my space, right? What happens is that the server receives the request, and it figures out that it has to run like an HTTP endpoint and the logger, and it will start them. So let's wait a little bit. I'm running in PWS, so let's wait until it starts. I see the log being received. The application is starting. Right. Container became healthy, so now I can start posting data to this, to the HTTP endpoint. And the HTTP endpoint is actually this other application that runs here, right? And I have different other options to do this. So for example, I can just do something like this. I can just scale. I can just say CF scale. Right. And I get two instances, right? Don't worry about the crash. It means something else. It means that the other instance is starting. All right, so I can see another instance starting right now, right? So I have two instances that receive data, and actually I can see that if I continue posting data, it will be actually a load balance between the two instances, right? So you see that app 0 and app 1 in here, and that indicates that as I continue sending data, if you follow the application number in here, it actually changes from 0 to 1, because actually it's like I get data shuffle, right? So that is cool, but maybe I don't want that related data to go to separate instances. I want to have this degree of control, right? I want to implement partition. So what I'm going to do is I'm going to redeploy the stream. And as you see right now, when I deploy a stream, and I actually can specify the number of instances of each application, right? So what I'm going to do is, by the way, I'm going to show you the UI just to see that the two applications that I've shown you earlier are gone now, right? When I deploy a stream, new applications are created, are deployed, are managed. When I undeploy them, we take care of actually cleaning them up. So now I'm going to do and deploy and redeploy this. And just wait a couple of minutes until the applications are already deployed. But by the way, when I'm looking again at the UI, don't mind the other applications. They're actually just some of the some of our test applications. But if you look at this HTTP log, you already see that it has a instance count of 2, which is what I requested in the first place, right? So when this process completes, which should be very soon, what I should see is that as I continue posting data as I start posting data to the HTTP endpoints. Oh, it's not started yet. Okay. I have to wait until the HTTP server is started. Of more instances, it takes a little bit longer. And this is running on a free plan, so not many resources, but it can handle them, and I have an HTTP server now. So, again from the top, you can see that when I send the same data, it effectively lands in the same application, right? If I send even numbers, they end up in instance 0, right? If I send odd numbers, they end up in instance 1, right? So basically just declaratively, I established like a data partitioning strategy for my applications, right? So this is essentially an example of how data flow like kind of materializes the DSL for data flow essentially translates those specifications into, let's say, Spring Cloud Stream application capabilities, and how it abstracts some of the details into a higher level DSL, right? If you'll allow me a couple more minutes, I'd like to talk about the last part, because I think it's interesting. Like streaming is sort of streaming is kind of takes a lot of time, but it's tasks that actually deserve as much attention, right? It's a shorter description because really what happens is, unlike streams which run continuously, tasks are short-lived. So it's easier to see them into a certain sense as microservices. They're very isolated. They're very they're standalone, right? The analogy here is that, and they're not services definitely because they don't run continuously. The similarity actually here is with essentially that tasks and the tasks built by Spring Cloud Task are also Spring Boot applications, standalone, and then have to share the same features, right? Let me just show you very quickly. So the programming model is very simple. It has the same enable approach as with streams. You put enable task on your application, and what you get is that every application is gonna record the state, record its state, and records its progress into a database. Like when it started, what was the task, what was the exit code, what happened inside it, which is exactly the kind of thing that we want to monitor for short-lived applications. So you can register these standalone jars in Spring Cloud in Spring Cloud Dataflow, and then you can just, like you have a DSL to launch them just as for streams. And two features actually come here which are interesting, and that's basically where my time is up. Actually, it's been up for a while, but I'm pretty excited about it, so I want to finish. It's first, these tasks, as they run, they emit messages. They don't only record what they do. They actually tell. So you can have a stream, for example, created out of the results of executing different tasks. And actually, that's a pretty interesting feature and pretty useful feature. And it's actually been around there for a long time. It's essentially if you're looking at Spring Batch and Spring integration interoperability, that's been one of the major features there, right? So we're just making that available at a higher level of abstraction. The other interaction is at the other end. So you can also have, for example, tasks launched in response to different events, which could be, for example, an HTTP request. An HTTP request allows you, for example, to integrate with an enterprise scheduler, right? You can have an application basically just send HTTP calls regularly whenever it wants to launch a task with specific characteristics. But it can be any other thing, right? And again, tasks can come in all shapes or forms, implementations. So we have, for example, Spring Batch applications, but they can also be, for example, not even like non-Spring Batch related. Like things like running Spark jobs and Scoop jobs and so on and so forth. And the last item that's probably relevant here is that all these things are kind of building blocks, and the ecosystem itself comes with a pretty wide range of pre-written applications, like a ton of integrations, which are basically, again, the legacy, and I'm using legacy, or actually not legacy because that's a term that you don't want to use, especially in this industry, but it's the inheritance of Spring integration, right? Like all that ecosystem is basically available through these out-of-the-box applications for different kinds of jobs, and they can actually are microservices. You can run them standalone, or you can orchestrate them through Spring Cloud Dataflow. So that's pretty much it. Thanks a lot for your patience, and if you have questions, please feel free to find me. I'll be here. So,
Very good. Any questions for Marius?
So the
Question at the back.
Sure.
Will it be fair to say that what you described is ESB 2.0?
Well, I thought that was Spring integration and Apache Camel, because like removing ESB is not necessarily ESB. ESBs have had a different. It's not an ESB replacement. ESBs have have routing and other features that do not necessarily match the like this particular structure, so to speak. There are similarities, but I wouldn't put them in the same category, so to speak.
One more.
MapReduce process. So, does this data processing? So, like
if there so the question was whether it has a MapReduce.
Yeah, process.
There is a MapReduce job, so there is integration with MapReduce as, for example, as a Spring Batch job. integration. So that Spring Hadoop has some of that.
Going back to your comment, how different is it from Camel?
From Camel?
Mm-hmm.
Well, first and foremost, Camel is a framework, like is an enterprise integration framework, right? So basically, it's designed for writing applications. Like really, it doesn't have any orchestration component. It doesn't have any multi-instance management component. So at that level, there is, let's say, no match with the data flow and the deployment part of it. When it comes to Spring integration, sure, Spring integration and Camel have been often compared, right? And you would put them in the same category, right? So the comparisons are there. Something like Spring Cloud Stream, essentially, and this is what I was mentioning earlier, we've tried to be an abstraction layer on top of that. So basically, you could use the Spring integration components. It's not, let's say, I hope that the Apache Camel, for example, had an abstraction layer. It would look like Spring Cloud Stream because these are the primitives and these are the, let's say, more opinionated patterns that we wanted to implement there, right? But I wouldn't necessarily compare them as such. Both of them do messaging, and both of them are messaging frameworks, but there are different. The difference is essentially in the primitives and in the abstractions that we've built.
I have heard like an opposite comparison where abstraction in Camel is much more and Spring is more primitive, it's more flexibility. Being primitive, it gives more flexibility and more options.
Well, I'm sorry. I don't want to make we can take this discussion offline. That's my point. We're trying to be opinionated. Spring integration is one thing. We're opinionated on top of Spring integration with this type of structure. So that's what I'm saying, that the comparison is not in that sense.
Anything else? Okay, round of applause.
Thanks. Well,
And thank you to all of our speakers. Quite a few of them are still left. Did everyone have a good day? Good sessions? Awesome. Awesome. Yeah, clap. Okay, so a couple closing notes. Please rate the meetup. So on the meetup, you can give the conference a rating. We want to do this again, so we're very interested in any suggestions. More chairs, more comfortable chairs. I know that already. So a few other things, I'm sure. So please let us know because we do want to do this again. Those who did Square receipts, the receipt that got sent out is like some kind of placeholder information. It doesn't actually say the name of the conference. So I've updated it. If you want a reissued receipt, just come see me. I just need your email address to do that. And that's it. So let's have the raffle. So, yeah, so does everyone? Okay, yeah. All right. So Nicholas is going to come and draw for first place. No, don't give me both of your things. If you give me, so if you only had one, keep it, okay? Because your other one is in here. If both are in here, you're never going to win. So hopefully no one did that. All right. So what should be grand prize? Fitbit Charge 2 or Galaxy Tab? What's better by applause? Tab or Fitbit? Tab, first place? All right. Nicholas, come draw it. So by the way, Nicholas is our recruiter. So if you want a job at Pivotal, he's also a guy you can talk to.
Nice. Thanks for letting me know ahead of time. Okay, so the winner is, let me just rattle off the number.
Oh, yeah, big number. Okay.
So it's 313-8103.
No, 3138103.
I think that's what I said.
Is that what you said?
I think so. It sounded similar to me.
I'm
but
pretty tired. Who's got
all
that?
good.
Oh, winner? Nice. Sorry, man. Totally fried. All right.
That's right, right?
I don't know. Clearly, I can't read, so yeah, that's right. Yeah. Okay, awesome. Let's get Jürgen. Oh, well, we're going to do pictures after. Jürgen, would you like to draw one? So this is for Fitbit Charge 2. So these prizes are courtesy of our sponsors, by the way. There we go.
chasing one down here. I feel it. I feel it.
Okay.
Oh, so.
Maybe you should do it.
Do your thing.
Okay, 3138165.
That sounds about right.
That person may have gone home. Another. No, you missed by one digit, buddy. Very close. Okay, so that person went home. Oh, that's all right.
Go on with this. Go on with this.
Yeah. Hmm?
Not sure
Nah.
that's right. So, one more.
3138. Oh, they all start like that. 147. You got it? All right.
Congratulations.
Congratulations. Nice. Okay. So this next one is one of these sort of battery packs. Who else can we get? Spencer, you want to draw one? Chris, closer. You can do fourth place. All right. There we go. Staples. So it's 106 is the last three digits. 106? Yeah. All right. Awesome. I'm just going to trust people that win. I say that now and the prizes are almost done. All right.
Beat the last four.
What's that?
The last four, you need the last three.
Okay. Who's going to do last draw? Spencer, you want to take it? So these are for a series of books. So there's a bunch. You can give them to your friends. It's cloud native stuff. How would you read it out? I'm getting wiped out here.
8107 is the last four.
8107. Going once. Oh, we got a winner. All right. There you go. Enjoy. So I hope everyone had a great day. Feel free to grab a drink before you leave, and thank you for coming.